Greetings everyone and welcome to RedisConf 2020. My name is Zohaib Sitte Hassan. I'm going to be discussing improving cache at scale. I am a technical lead manager at DoorDash. A little bit of introduction about myself. I'm an engineer. I'm a philosopher. I'm a father. I love open source software. For those of you who would interact with me, you would find me extremely opinionated. People have a love-hate relationship with my opinions. So I won't blame you if you are bothered by my opinions at all. So my association with Redis goes way back. These are just a bunch of articles. I guess I don't even own the domain anymore, but these are a bunch of articles that I wrote way back. This is around Redis hardly being version 1. Somewhere in September 2011, October 2012. I was working with a company that was building these complex pub/sub mechanisms, doing end-to-end chat-ish behavior, I would say. And it required quite a lot of publish subscribe and holding data into the cache so that the real-time data can be served out of the box really quick. So I started working on Redis. Before that, I was working with Memcache, and what I noticed while using Memcache was like, hey, my whole job would be a lot more easy if I have a dictionary or say a sorted set. And turns out Redis was just around the corner at that point in time, and it was nice to see a data store that is providing me all these data structures, but I wasn't sure. But as the time went by and I started using it, the more I got comfortable, and eventually I kind of, fully adopted the embraced, I would say, the Redis philosophy. Not to mention, this is the era when NoSQL was pretty hot buzzword, so I was being very cautious about picking which store should I use and where should I use it. Not to mention these two posts that you see. So one of the things that I was trying to achieve while doing my first post, A Journey to the Center of Redis, was looking at the code and plumbing a mechanism in Redis to say, hey, whenever a key evicts, do a publish on a particular or on a configurable channel name. I even did a PR that, so you can look at that. It's around 2.2, and it was although it was it was a good experience, but it was in no way kind of production ready. Today you have that mechanism already in Redis now, where you can set out to say, hey, whenever a key expires or evicts or anything happens like that, you can get those events on a publish subscribe. And I'm going to talk about this more towards the end because there's something similar coming in next version of Redis. So this is about me. Like, this is what I've been doing over time. You can see the pull request is around September 2011. So it's almost like what almost 9 years now. But that's how long I've been working with Redis, and I've been associated to the community. So right now, I'm working at DoorDash, and for those of you who don't know what's DoorDash, well, some of you might think of it as a food delivery company, but DoorDash is more than that. DoorDash is about creating a delightful experience, especially in this harsh time of COVID-19. I think DoorDash is sitting at the center of all these things happening, and supporting merchants and keeping people safe. And when we say creating delightful experience, it means we want to provide you with an experience where you while you enjoy your food getting delivered to you, at the same time it can be done at a large scale. So just doing this problem at a huge scale where we can deliver almost anything to you, the last mile delivery part, is where we're focused at. And it's a hard problem. It's interesting, and it gets very interesting when you have millions of folks hitting your website and you're trying to serve them all menus at the same time, getting the orders working, and it's a huge complex machinery. So these are a bunch of learnings that we have done while we've been trying to build and scale our systems at DoorDash. Um, the way I see it is, after a certain scale, um, you would start paying attention to, like, hey, how this particular piece is working, and if there's an inefficiency in there, or after an outage, you would realize, oh, this is why the whole thing went downhill. Uh, all of these things that you're going to see are going to be the learnings that we have gathered over time, from our experience. And we're going to start off, or one of the most important things that we've seen over time is the CasteMP problem. So CasteMP, it's also known as cache miss storm or a thundering herd problem. It's a pretty well known problem. For those who don't know what's a CasteMP or thundering herd, here is a simple example. So imagine you have two servers, and you have cached something in Redis. Now, when a request comes, in the initial part, the two requests are directly served off from Redis. That's where you see those green arrows. And we were able to serve off the request directly from the Redis perfectly fine. But since servers are distributed and lots of requests are being served through these servers, the moment this key expires, all of these servers, at that very instant, are going to go to Redis and say, hey, give me that particular key that I was looking for. This could be anything. This could be your cached menu. This could be your user info. This could be your country code, anything at all. Now, what happens is, since the key expired, all of the servers get back an empty response or a null from Redis. That's where you see those red arrows. And these servers being acting like a read-through cache for them, they immediately fall back to the database. So you see those blue arrows heading to database. And not only these blue arrows are duplicate reads, but this is going to cause problem when you're serving requests in hundreds of thousands per second. You're literally going to slam your database with all this traffic, and you're obviously going to observe a latency increase. That's not where the damage stops, actually. So after reading from database, since everybody is going to write back to the Redis, so everyone is now doing a duplicate write back into the Redis cache itself. So a stampede or a herd is a phenomenon where, due to in case of Redis, due to cache miss, we're causing a stampede or a thundering herd on database. So how can we solve that? What's a typical approach that's taken to solve this problem? So yeah, duplicate reads everywhere, and you're gonna see these reads even on Redis, duplicate writes on Redis, duplicate reads on database. So that is the main problem that we're trying to address. So in order to fix this problem, imagine a virtual expiry in a fixed random gap. So say your key your key or the entity that you cached was valid for say 15 seconds. So we would imagine a 2 second or 1 second or however many seconds. Let's imagine 2 second gap. So if you have a window of 15 seconds during which the entity is valid in cache, we take the last 2 seconds and treat that as a gap for ourselves, where we're going to do something fancy. So we have the given timestamp. So if you know where the entry was created, and we know the TTL, so it was created say 1 p.m. for 15 seconds. We have the TTL, we have the timestamp, and the gap, let's say in this case, is 2 seconds. We will consider a key expired if the timestamp plus TTL plus random into gap. So the important part here is the random into gap is greater than now, right? So this is artificially adding some random number. It's just like a jitter. And we're adding that number to cause this particular if check or this particular condition to be false from the client side. So there's nothing fancy happening on Redis right now, but from the client side, we kind of simulate saying, oh, I'm just going to do, a rand toss and multiply it with the gap. So rand since can be between 0 and 1, and if it's 2 second, your random eviction window or the gap is going to cause this last 2 seconds to, at random from different servers, cause to tip over the servers to think that, hey, the entry has already expired. So that's it. We do this, and with this random, we imagine that, hey, this entry has already expired, so let me go ahead and read it from database or whatever your secondary logic is to prefetch the item. So simulating the same ahead of time expiry in Redis is pretty simple. So here's just a very basic code that I just put together in Python. This is not our production code at all, but this is totally something that would work. So if you look at it, the first line, so fetch AOT is the method that takes a key and the expiry gap in milliseconds. What I do here is I say, oh, Redis, give me a TTL. PTTL is going to give me in milliseconds a TTL of this cache key in milliseconds. So remember the TTL is the time left from Redis. It's the amount of time instead of it's a little bit different than the approach that I described, but it's exactly the same thing if you think about it. So TTL milliseconds is going to give you the number of milliseconds that's left for this key. So I read that TTL, then I subtract the random, and random is just a function that generates random, and multiply that with the expiry gap. And if that TTL is greater than 0, means there's still some life left in this key even after getting rid of that expiry window, then I read the key from Redis. Of course, you can have pipeline and all that to make this whole round trip a single shot instead of 2 round trips. Otherwise, I just return back a none. So as a usage, what I would say is, hey, fetch my key foo. 2000 milliseconds, it's the time of my gap. So what would happen is at random, 2 seconds ahead of time at random, some of the machines would get an eviction, a simulated expiry eviction, and they would go ahead and read the original value from database. The main idea is that if fewer number of servers can go and read from database, it would cause lesser number of connections going, or the requests going to the main database, and hence reading that data and populating the cache with fresh data causing the rest of the herd, the rest of the huge amount of the requests that are coming in, to kind of prevent that and cut that off before the damage happens. So we can stop here and say, yeah, at random we can do this, but at DoorDash, remember, we go for excellence. So we ask for ourselves, like, hey, can we do any better than this? And turns out, yes, we can. Here's a paper called Optimal Probabilistic Cache Stampede Prevention. The URL is on the top, and this paper is all about how one can improve this probabilistic expiry that we did. It's a really nice paper. What I'm going to describe here is, I would say, a very distilled version of it, but this paper goes pretty deep up to the point it does a proof, a lemma proof on why this method is more efficient. And what this paper proves is like, hey, so for example, here's one of the snapshots from the paper where it shows you like, hey, if I'm doing these uniform the distribution based evictions of 10-second windows, this is the stampede size that we notice. So purple and orange are the eviction or uniform using uniform random number eviction that we just saw, and the green one is the technique that they propose. And if you go a little bit deeper in the paper, it gives you pseudocode for doing this cache read as well. What I'm going to do is I'm going to leave this for everyone else to kind of go and read through. But what I'm going to give you is a very distilled version of this exact same thing. And the only thing that you're going to notice here is this one log random with an expiry gap and a beta. I won't go into the technical details, but you'll notice a couple of things different here. So how does doing a log random changes it? I would say it's more of a mathematical thing, and I would ask everyone to please look at the paper again. But with the beta and the log random, we are able to distribute out this ahead of time eviction way cleanly across the timeline. So just by changing from random to a log random, we're capable of we're able to reduce this load quite significantly. So and you would also notice where instead of minus, we're doing a plus in TTL, because the result of this thing is always a negative number. And where that only if the key is not considered evicted, only then we kind of read it from Redis. Otherwise, we consider it kind of expired. So according to paper, this is the improvement you would usually see in the Stampede with the 10-second window. And it's very interesting that the green line is the one with the proposed method, which has a pretty low stampede size, and if you look at the orange one, it has a pretty high stampede. It's a large gap. It won't look like much over here when you're doing it for a small number of servers, but when it goes pretty high on a large number of keys, all of this adds up. So this flattening of the line adds up significantly towards how much load your servers get. So before we wrap up with this, one more thing we want to do, and that's like in a typical application, usually most of the time at least, there is also an application cache that's like an in-memory cache that everyone has. Consider this cache like an L1 cache, and if we consider Redis like an L2 cache, so there are two levels of cache now. So the stampede that you just saw between database and the L2 cache, or the Redis itself, is going to replicate itself between L1 and L2 as well, because yeah, as long as you're reading from a source and that source expires at a constant time and everybody rushes out to read the same value, it's going to cause a stampede. L1 caches are usually very small in their nature, but sometimes they are pretty large in terms of their lifespan. It totally depends upon a scenario, but in cases where you can actually use L1 pretty significantly, and these are usually the scenarios where it's extremely read intensive situations. In that case, the same problem would occur between L1 and L2. So every time, think of this as every time you're touching a network and you're going across the wire, there is a problem. And we want to make sure that when people go out and they start reading the values from different sources, they don't cause a stampede. So we can kind of, under high traffic load, similar CasteMP with mistorm can be observed between L1 and L2 and so on, right? So each level would have the same thing. So we can rinse and repeat the same solution here as well. So you can say my L1 is also going to do ahead of time eviction. Combining just these two techniques where we're just doing ahead of time eviction or expiry, simulating, I should not be using ahead of time eviction all the time, where we're simulating an ahead of time expiry or eviction, we notice a significant difference. So everyone is familiar with this graph where you have this spiky nature because the key, and so this is between the L1 and the Redis itself, but you would observe the exact same pattern between Redis and database if you're doing the read through. So everyone recognizes this pattern, spiky nature. Although Redis works pretty well, but what if I told you by applying these techniques, you can get something like this? So notice the difference every time, and it's all of these graphs are from pretty high traffic windows. I won't disclose where is this coming from, but the previous graph on the top is when there was no ahead of time eviction or ahead of time expiry being simulated on L1, and the one at the bottom is after we applied the fix. So this spiky nature that you see on the top is a typical thing that you would see on database and Redis, and that's a perfect indicator of saying, thing expires and everybody rushes in to read, and due to high traffic, you would just see pretty high peaks. In this case, they were around 9K, and at the bottom there, the moment we introduce this mechanism, it's like 22, 30, 28 worse, which is pretty encouraging. Think of the amount of round trips each of these services saved and the amount of latency improvements that you would see just by doing this. The next technique that we kind of figured out was debouncing. So debouncing is a pretty well-known technique in front-end world. So debouncing is the fact that, hey, so for example, if I'm reading a full key from a single server and there are 10 requests coming in at the same time to read the full key, what you're going to end up is with taking up these 10 requests or network round trips when you could have done only one, because it's a single server. So if you're reading almost at the same instant, you're most probably going to read the same value. But due to the disconnect between all these threads and everything, so imagine even after applying the previous technique on L1, 10 of these requests graduate into saying, hey, we're going to go ahead and read our value from Redis because we simulated cache miss or cache expiry, right? We took this approach where on bunch of platforms, especially when in a single process there are multiple threads or multiple request handlers trying to handle multiple requests. You can kind of use this technique of exploiting promises. Sometimes they're also known as deferreds, tasks, futures. Each language has its own terminology, but essentially it's the same idea that I did a promise to you that I'm going to go read this value from the server, and if somebody else is interested in the same value, I'm going to return him back exactly the same promise. So at the same time, if there are 20 requests coming in trying to read the same thing, there is one promise sitting in front of all of them, and that one promise is just fulfilled by one request, and that's it. I think it's better explained from the code. Let me first go through this on how we're going to break down our problem. Every reader provides an L1 miss function. So you're picking up from L1, but every reader should provide an L1 miss function. Usually this function is same across everyone. If this function is reading from database or Redis or somewhere else, the logic is exactly going to be the same across all the clients that are reading. So the function is exactly the same. So when invoked via debouncer with an ID, given ID, only the first reader is allowed to execute. So in case there is a miss, only the first function would start executing and it would return you back a promise. So the rest of the readers that are coming in after the first winner immediately get back the promise that this L1 miss function returned in first call. And all readers then wait on these promises to say whenever the promise is satisfied, I'm just gonna make progress in my code. So subsequent calls to ID will call L1 miss function as soon as the promise has been resolved. So the promise only lives during the duration of it being fulfilled or rejected. And only, so say if there was a pending call for ID that's taking 2 seconds, so during those 2 seconds, all the calls for this particular ID are going to hook on to the same promise. So it's extremely important that your function can, you satisfy all the requirements of saying, hey, L1 miss function fails open quickly. There's a good retry logic because the functions at the back or the callers at the back are waiting on you to provide the value. So we need to have all this fault tolerance in this function, but the advantage that you get is only one reader going ahead and doing the read, which usually would cause lesser load and hence causing a lesser chance of a load on your database or your Redis. So I think it would be much easier to explain with the code, as I said. So this is how we imagine the API first. So here's a debouncer. The function, the async function menu item loader, takes a key, reads it from Redis or database. Imagine that code is in there. So all we do is every time we want to read the value, we say debouncer.debounce. We provide it with a key. So this is the exact same key that's passed down to the menu item loader or the loader itself. And then we await on that promise. So the menu item loader itself returns back a promise. And if you look at the implementation of debouncer, it's that simple. It's a simple constructor that keeps a pending board, like pending board as in the ID to promise pending. When you call debounce, it says, oh, if the ID is not already undefined, means somebody is already trying to fulfill the promise with his execution, just return back that promise. And otherwise, you call the callback that came to you, which is going to return you back a promise, and then await on that promise. And then finally, once the promise has been accepted or rejected, we don't care. We delete out that ID, which is going to make sure that our board doesn't keeps growing infinitely. So it's a very simple implementation. This is a JS version of this implementation. You can do a Python implementation. You can do maybe a C# implementation with the tasks. You can do a Java implementation with the futures. It doesn't matter. The core concept is exactly the same. You return back a single promise for a single entity, and the duplicate readers are going to wait on that promise or the future or deferred or task or anything at all. And what we actually did was we wrote a simulator. You can actually go to this URL, run the simulator, and you would see the difference. You can actually play with the different parameters, tune it out, and see how it works. It's pretty significant in terms of impact that we see. In case of Java, I wanted to specifically call out like a lot of libraries. It's not a novel idea usually when you're doing these kind of things. So we are always up to kind of looking around. Hey, if somebody else did it, and if we can use something out of the box, that would be great. And turns out Caffeine is a really nice cache from one of my friends. He has done an awesome job in terms of both performance and everything. And it has a built-in thing called loaders. So the line at the bottom in the build where it takes a key and says create an expensive graph, it's an example directly posted from the wiki that they have, and this is already doing the exact same mechanism that I described. So it's not a new thing. If you're not using Caffeine, would highly recommend use it. It's a really nice cache with high performance, and I kind of enrose it, to be honest. So doing all these optimizations with ahead of time and all that, we configured our servers like a 2pod, and we did like we run our benchmark tool. We use ghertz for benchmarking. Our L1 cache was 5 seconds TTL. L2 was 10 seconds TTL, and falls back to Postgres to read the users. And we did a repeated cycle of bombarding our servers with requests. And we did it for 60 seconds because we wanted to see multiple evictions happening. And we didn't apply any rate limits. So before the whole debouncing, we were doing around like 17,000 requests a second. And just to call it out, this is doing a whole read through from your cache to Redis to database. So just remember, without debouncing, just with AOT eviction, this is the number that we were getting because it's already so efficient. And with debouncing, you can see there was a significant jump, almost 21, from 17 to 21. And the other important thing to notice here is the average has dropped. If you look at the average, it has dropped, and same is true for the slowest request. The slowest request without debouncing took like 8 seconds because a lot of readers piled up, and now database or Redis was struggling with keeping you up with the value. But with debouncing, you can see most of the times the process, even if there was an eviction, the process just held on to the resources from the single promise and quickly returned back. So this technique has also helped us scale our service quite a lot. And I would highly recommend if you're writing Java, go look at Caffeine. And if you're doing Node.js, I already gave you the code, which is much simple. I'm pretty sure you would find something similar for Python as well. Worst case, it's that simple to implement. Let's talk about large values. This has been an interesting topic for us because why would you need to store large values? Let's think about all the cases. I can point you to the case where we're using it. We're using it to cache our menus, our search results, our profile information, for example. And these are usually large JSON payloads, especially menus are like huge JSON payloads. And I'll be showing you in a middle, like in a moment, exactly how large they are. But people also use it to cache like machine learning models. People actually use Redis with, turning it into a queue, like projects like Sidekick and all that. And even more use cases are going to open up because Redis streams and message payloads are going to be extensively used across this whole ecosystem. So the argument of why we should worry about large payloads is suddenly going to make sense, because you're going to need large payloads to be, efficient as much as they can be. So we took a page from HTTP and decided to use compression. We didn't started doing, oh, let me go out, write an extension of my own, do something magical, optimize protocol, anything at all. We said, okay, this is what we get out of the box, how we can improve on top of this. And turns out compression can help you a lot. This is how precisely HTTP works, right? And it's a well-known, well-tested thing. So these are the considerations while considering a compression algorithm. We wanted to provide a decent compression ratio. Not to mention, when you say decent, it means I don't want it to be the highest compression ratio across the board. I don't want that. I want a decent amount of compression that can reduce my payload size, with the constraint that I want this whole thing to be lightweight on CPU, because I'm doing too many requests. I don't want my server to bog down. And for us at DoorDash, because servers are already pretty CPU intensive due to the load they're handling, we can't risk ourselves of saying, hey, oh yeah, just by adding this one compression, we shot our CPUs by 20%. This is significantly going to add to the cost, but at the same time, it can cause outages and problems. So we wanted something lightweight, and we wanted something stable as well, which is well tested and well maintained by community, instead of inventing something of our own. So what did we do here now then? So meet LZBench. By chance, there is a good website out there that can give you a comparison of all these compression algorithms with their nice times on compression ratio, speed, and decompression speed. For us, what mattered kind of the most was the decompression speed, because our scenarios are very, very read intensive. But you would notice that the compression technique that we picked is also good for write scenarios as well, because it doesn't cost much even to compress. But it still gives you a good or a decent amount of compression ratio. Disclaimer right here, this whole compression technique or the compression algorithm that you're going to pick is going to totally be dependent upon the type of data that you have. So before you pick one, I would highly suggest use the site, you do the benchmarks at your own. And this is how we landed and figured out, and I'm going to show you how we landed and figured out which one we want to go with. But there are a bunch of tools already out there that built by community, which gives you a pretty good insight into this is what you should be using. So in our scenario, for example, when I said our menus are pretty heavy, just to give you an example, Chick-fil-A's menu is like 64 KB. Well, some of you might be, it's fine, but catch that. Cheesecake Factory's JSON serialized menu is 350 KB. Now, it's not that heavy to ship it over wire, but when you have thousands and hundreds of thousands and millions of stores, this starts to matter, and especially after the fact that there are variations of these menus that we want to store. This size is going to act like a multiplier to us, and that's why we wanted to attack the crux of the problem. If we can cut down on the size, that would mean we're going to cut down on the amount spent on network. Again, and whenever you're going on network, think about it. If we cut down on our size, time spent on network, we're effectively optimizing the cost. And CPU is going to be cheaper in terms of the amount spent versus network transferring these many bytes again and again over time. So just to simulate this in your head, if say we're serializing Cheesecake Factory's one type of menu of Cheesecake Factory, and we're doing thousands of requests per second for this single menu, you can see what kind of havoc this thing is going to wreak. So these are like this is just, I would say, a sample of what we have to see every day in terms of traffic insights. So we took these menus, we started compressing them with different algorithms. We settled down on LZ4 versus Snappy debate. What we noticed was LZ4 has a slightly higher compression ratio, while compressing our serialized payloads on average, LZ4 was 38.54% versus 39.71% of Snappy. And this is a uniformly distributed menus that we were trying to compress. Compression speeds of LZ4 were almost the same. At some paces, it's fractionally slower, but the decompression was like, it just smoked Snappy out of the water. And it was just, too fast, 2 times faster than Snappy almost. So we decided to settle with LZ4. And just to give you an example of 10,000 similar operations in terms of set, you can see, so this is us taking serialized menus and just doing plain get set on Redis, just to observe the time on how much time it takes. So without compression, you can see it took like 16.5 seconds. With Snappy compression took 12.6 seconds, which is a good significant drop. LZ4 almost the same, 12.8 seconds. In case of get, you can see that's where we burn most of the fat off. Although the set is also a pretty good number, but get is where we're getting the real benefit here. That's why I mentioned it totally depends upon your scenario. So make sure you understand your scenario really well. Usually without compression, get was taking on average 12 point something seconds, and we did multiple runs of these 10,000 keys. So this is just an average of all those numbers. And Snappy took like 7.56 seconds, and LZ4 took like 6.4 seconds, almost a second less than Snappy. Hence adding to my point of like it was way faster as well. So we made the changes to the code. We slowly rolled it out in production so that we don't break it, and here are the results. Pretty encouraging in terms of traffic drop that we see. So this is the traffic that was being shipped between our servers and Redis. You can see it almost halved itself. It's almost half. And this is precisely what we were trying to achieve. And the latency is also dropped. So uncompressed, you can see how spiky. We would usually see these random spikes in the middle due to something happening on network and all that. But after that, that pretty much went away. And the P99 times of doing these multiple calls, compiling all that data, availability, pricing, all that, the endpoint overall reduced the latency pretty significantly, almost like 25%, just by introducing this technique. So yeah, in conclusion, compression is a valuable technique, well tested, well understood. Everyone should be doing that. You do it all the time on HTTP. Why don't you do it between Redis and the server as well? Let's talk about hotkeys, and it's one of those topics that come up pretty significantly. So what is a hotkey? I guess most of you would already know. For those who don't know, that hotkey is where you have a shard or like a different partitions in case of Redis, and one of the partitions is hot due to one key or few keys being read from the same partition again and again. This could be something that's read pretty heavily, like thousands of times, or maybe hundreds of thousands of times a second. So what's happening is now one of your Redis nodes is running really hot, and rest of them are just slacking. And sometimes for these scenarios, you can't cache these kind of things in L1 cache. Point being, you're verifying a user token, and we have a good flushing pipeline to say, hey, flush out this user information the moment he is the moment he changes his password, for example. And same is true like country code, for example, country locale information, or promo marketing going on in a region against region ID, or storing that information. I can keep going on and on with examples. There can be cases where you don't want to put it in the in process or the L1 cache. And what the effect of this whole thing is causing a high CPU usage on a single partition. So your one partition goes crazy, and the rest of them are like not that high on CPU. And this is for read intensive operations only. The technique that we're about to describe is effectively good for when you are doing read intensive stuff. People might complain like, hey, it's slower on write, but that's what the intention is. It might be a little bit slower on write, but the main gain we're trying to achieve out of all of this is making our reads extremely fast. So what can we do in this case? So some of you might say, yeah, one partition is like master is running hot. Why don't I add a bunch of replicas? And then these replicas can be the point where I distribute out my reads. It's a classical database approach, totally doable. Sometimes the client libraries, to be honest, don't have the support, or they're not sophisticated enough to distribute the whole thing evenly in cluster configuration. That's where you might want to take another approach, which I feel like is gonna give you more bang for your buck, because still one of your partition is loaded. In case of failover, there's a higher chance that you can get yourself bottlenecked and get yourself in a trouble just by sticking to one partition. How can we distribute this out evenly across different nodes? So how about say we have, in this case, imagine you have 3 partitions on Redis, right? So, and each one of them has a replica. It might be without replica as well, doesn't matter. But usually in typical configuration, cluster configuration with sentinels and all that, you get this kind of configuration where you have like 3 masters and 3 replicas. And what you can do is, what we should be ideally able to do is, we should be able to read from all of them. That's where we want to go, right? So turns out we can exploit the Redis key hashtag. Normally Redis would use the hash of the whole key to determine which slot it goes to, hence it determines which server it goes to. But if braces are present, it will use the value within the first braces. There is a complete rule around it in Redis. Only the first braces, the first starting curly brace and the ending curly brace, the value within that would be used. If there is an empty curly brace value, then it won't do it at all. You can read all of that in the Redis cluster documentation. It's documented pretty well. So for example, if we had a key called DoorDash, usually Redis would use CRC16 to compute the hash of DoorDash, the whole key itself. But if you have in braces copy-0 of DoorDash, then it's only going to use copy 0, hence the copy 0 is read. So and the copy 0 is basically the one that's then deciding which partition this key value is going to land on. That should ring a bell. So what if I make multiple copies of this, and if I say, hey, copy 0, copy 1, copy 2, and put it against same suffix, but just prefix my value with this key hashtag. So what would happen is we would be able to kind of ideally distribute due to the due to the even nature of the hashing, we should be able to distribute out these copies into our Redis instances, Redis masters across the cluster, which in turn would automatically get replicated down to the slaves as well. So how can we do that? I think it's pretty simple. So whenever you want to generate write keys, say imagine I have a method. So it's just an example method where I say, hey, write keys, here's a key, and here's the number of copies that I want, and it gives you back an array of keys that you should write against. So say if you have a cluster of 3, ideally you should be able to just generate 4 copies in order to make sure that everyone is touched once, and then just write out the values to those masters, and hence the replicas would get the values as well. Now when you want to read the value, what you do is you do a rand range. You generate a random between 0 to copies, and if each server is going to do that, it's again relying on the basic principles of probability, where it's backing itself by saying, hey, I'm going to generate a random every time. That's going to give me, among these 3 servers, a random place where I'm going to go and read my value from. And once you know which partition to go read from, then you can do a random again on between master and replica as well. Every write would write multiple copies of key value. That's where people might argue, hey, it's inefficient, but you can make it efficient by compressing and writing the values once, because this value is going to be read many times. So it's worth paying the write cost upfront. Every read picks a random copy to read from, so it goes to a random partition, reads the value from there, and then returns you back the value. Almost uniform by default, and I'm saying almost uniform because CRC 16 should ideally be able to distribute it pretty uniformly, but you can end up in a situation where 2 copies landed on the same partition, but you can always make your client more intelligent in the sense that if most of the Redis libraries, they do give you like, hey, given this key, which partition this is going to go to. So you can kind of skip or dedupe those things out by making client a little bit more intelligent. But even without all that logic, let's say, because this is a high availability scenario, we're okay doing the duplicates. Because we're already doing duplicates across the cluster. If you're paying the cost for saying, yeah, I would put storage in front to get high availability. So yeah, sure, why not? You can have multiple copies of these, even maybe sitting on the same node, doesn't matter. But what can happen is now every time when you're getting a read call, you go to one of the random slots and read it out, which ideally would even out the CPU across the cluster for extremely high payload stuff. Again, the examples I quoted were like, say, a promo going on, and people given a region ID, you're looking up promo details. So totally doable with this approach. I want to close this whole thing showing you the future and why I am very optimistic about this. All these techniques might either have to go away or might improve your system even further with what's shipping as part of Redis 6. So in Redis 6, the RESP 3 protocol is coming with a new server assisted caching. So this is where clients can say, I read this key from you, please let me know if something changes on this key, and the server will let you know about the slot. I've linked the documentation page, well documented. It's an extremely important step towards reducing the number of round trips, I would say, and it will improve the ahead of time eviction technique that I described for L1. And yes, L1 is going to be your best friend pretty soon. This would definitely help cut down a lot of traffic, making responses almost instantaneous. The other important progress I think that this thing is making is around the proxy. So Redis 6 is going to come with a proxy that's going to take care of routing the requests for you. Right now, a lot of clients are loaded with these different variations. I think the most painful point that I've noticed over time is client implementations having inconsistencies or not doing full spec implementation, and then when you're looking for that goodness, it's just not there. One example being some client implementations in Python not being able to read from multiple replicas evenly, or some don't do reads from replicas at all. Example being Redis. I don't want to call out anything, but Redis doesn't support reading from replicas at all, and you're stuck with masters. We had to go through this huge pain of migrating from Redis to another client altogether in order to make sure that we can distribute the load evenly across the clients. So with proxy, all of this would go away because we would be able to configure this in a much better manner. And the people would be implementing a simple Redis client where it's just doing a get set, and they don't have to deal with the complexities and details of like, hey, how would I pipeline these multiple requests across these multiple servers when one of them is down? How does the failover happen? What happens to the rest of them? I think this proxy is going to make a lot of difference for developers and make our lives a lot more easier. And my favorite of them all, the IO threads, the great complaint that everyone had for the longest time, where CPU is not being utilized because Redis is by default, by its nature, single-threaded. So it had one event loop for doing one thing at a time, and lots of libraries argued, authors and people argued about it. There's no point of keeping more than one connection from single app to Redis. And yeah, all of that is going to go away, and this not only kind of improves CPU utilization, we've already seen higher throughput results. If you follow the author of Redis on his Twitter, he's been posting the results, and they're mind-bogglingly good. So I'm pretty optimistic about the future of what's coming, and how Redis is going to improve your caching life and making your servers faster. I would like to wrap up saying thank you to all. Please feel free to ping me. My Twitter handle is in the video. You should be able to reach out to me over email, over Twitter, any channel. And I'll like to open up for questions if there are any.